let's actually walk through this. It's a tough problem, so let's actually walk through it. So first of all, like I said, let's figure out what we're trying to accomplish. This is like a step 0, right? We want to calculate the electric force on one of these charges, right? So what tools do we have to work with? We know that if we're going to be calculating electric force, we're probably want to use Coulomb's law. So we go ahead and write those out. Sorry, that's a little too quick. Right? So we have these tools that we're going to work with. What information are we going to need to use these tools, right? It's kind of worth it when you're kind of starting to get used to do these problems to take these one step at a time. Let's look at this thing. I know I want a force, so I need all this stuff. This is just a constant. I need to know the charges given, and I need to know the distances, right? The separation between the charges. So the question is, I need charges, distance, and the Coulomb constant. Do I have all the information? Mostly, right? They did not give me R, right? In this diagram, they show me this, but they don't give me this, right? So we take one step backwards. We say, okay, well, I know I'm going to need R13, and I know trigonometry, so I know I can figure out x squared plus y squared is equal to z squared, right? So now I have R31, just using a little bit of Pythagorean theorem. So now you look back and say, yes, I have everything I need to do, so now it's just plug. All right, so we define our coordinate system. We have x and y. We make our clear diagram, done. We list the known quantities. Make everything nice and easy. We calculate the magnitude of each force individually using Coulomb's law. So we got F21, F4,1, and then F31 that we calculated using the R that we just got from Pythagorean theorem. Okay? Then we need to determine the direction of each force. But we kind of walked through that while we were doing it qualitatively, right? Yes?
Just read two articles on just the first top two and then why. How do you know which direction it's going? Because they're repelling each other, right?
The what?
They're repelling each other, so how do you know which way it's going to go when they're
Okay, so you're asking, if I look at just this pair, how do I know what direction Q1 is going to go? So that's where you have to know that opposites, if you're just thinking it through, that opposites attract and like charges repel, right? So if we imagine this guy is being glued down in place, right? Because in this problem, remember, we're doing electrostatics, right? So we're not going to let everything keep changing on us because that just becomes a very, very complicated problem. We say this guy's pinned down, this guy's pinned down, this guy's pinned down. How does this guy move? Well, if it were just these two, and that's pinned in place, then that is going to move up because they repel each other.
So we're just looking at Q1.
I'm just looking at Q1, right? And that's an important, you see how these problems can get like really cognitively difficult if you don't focus on what it is they're asking you for, right? You can start to get, there's just a lot of stuff floating around, so you really do want to make what do they want and what are they not asking me? Okay, but then also when so that there's that, but then there is this, if you write down Coulomb's law accurately and you use the charges where a positive charge has a positive sign, negative charge has a negative sign, then out of the math will come the correct direction, right? You don't necessarily have to be sitting there thinking positives, likes, attract, and all this stuff, right? That thinking went into developing that formula. So you can trust the formula. But you only want to trust the formula once you know how the formula came about. Okay, so we got the three directions. We talked about y already, opposites attract and stuff. And we have their magnitudes because we just calculated them. And now we use vector addition, which we just walked through moments earlier, so we won't belabor this. Right, and we get the two forces. Okay, so the x component of just this guy acting on this guy acting on, this guy acting on this, which is 0. The x component of 4 acting on 1 is just f minus 4, 1, and I can now plug in those numbers I just calculated a moment ago, right? And this one we got that 0.707 because of the cosine of 45 degrees. So it's a lot of stuff I'm throwing up. I'm trying to put them up one at a time so it's not overwhelming. Is it too fast? Anyone? No, okay. Make sure you let me know. Okay, so we now have our x net and fy net in terms of real numbers, right? It's no longer just some weird unit where I say 1, right? These are actually in microcoulombs, right? Or here would be millinewtons. Right, so then, here's a slide that was missing. The final net force is just x squared plus y squared equals z squared, right? You have an x component, you have a y component, so the final direction, in that final direction, you have the magnitude of it being the square root of fx plus fy each squared. Right, plug in the numbers, and we get 8.2 times 10 to the minus 3 newtons. And then finally, if we need to calculate direction, right here it's a little bit obvious because by symmetry, because this was equal to this and this is equal to this, it has to be going at 45 degrees. But if we had said, oh, what if this is 0.9 microcoulombs, right? And this one's 1.1 microcoulombs, then it's no longer symmetric. So then your intuition's not going to get you there, so we got to do the math, right? So if the tangent of the angle is the rise over the run, right? And the amount it's going to run is f, the x component of the force. The amount it's going to rise is the y component of the force. Right? So F force y component over force x component is the tangent of this angle. Right? But remember what you're doing. We've drawn these forces. You know it's pointing that way. I'm measuring this angle with respect to what? This direction. Right? That's not the standard direction that I gave you on that polar plot. Right? But we're not worried about extra factors of pi and all this other stuff and atan2 in your calculator and all this other stuff. We're just going to do it easily graphically. And we know that this angle, we're just going to calculate this angle, is the rise over the run. And that angle, when I plug in those numbers, gives me 45 degrees. So this angle is 45 degrees. But if I actually ask you, if somebody were to ask you, what is the angle in the global coordinate system, right? If we go back to our polar plot, this was 0 degrees, this was 90 degrees, so this is going to be 180 minus that angle, so that's 45, or I'm sorry, 135.